2023 problem solving session on signals and systems. Welcome to Signals and Systems Gate Problem Solving Session Part 2. Let us see the question. Given x1 of t like this and x2 of t as shown in figure. For y of t equal to x1 of t and convolved with x2 of t, we have to find integral minus infinity to infinite y of t dt. First, take x1 of t, u of t plus 1.5 minus u of t minus 1.5. Delayed steps. U of t plus 1.5 is, it starts from t equal to minus 1.5. So let it be 1 and let it be 2, minus 1 and minus 2. So this is 1.5 minus 1.5. So the step starts like this. This is u of t plus 1.5. Same way u of t minus 1.5 is, this is 0, this is 1, this is 2, minus 1, minus 2. This is plus 1.5. It starts, this u of t minus 1.5 starts from 1.5. So the signal is like this. As both are unit amplitudes, 1. Now we'll draw the signal. You have to subtract this u of t minus 1.5 from u of t plus 1.5. So this is u of t minus 1.5 and this is u of t plus 1.5. Just if you shift this and you subtract the remaining part, the output is like this. This is u of t plus 1.5 minus u of t minus 1.5. This is 1 and this is 1.5 and this is 2. And this is 1 and this is 2 and this is minus 1.5. So the signal is like this. So that is x1 of t. And already given x2 of t. Now we will write what is x1 of t. x1 of t is a rectangular pulse. Okay. And the rectangular pulse width is totally, this is 3. So you can write this rectangular pulse as a rect of t by 3. Rect of t by 3 is nothing but your x1 of t. And what about this x2 of t? See here, x2 of t consists of two impulses at minus 3 and 2 and one rectangular pulse. So totally your x2 of t can be written as delta of t plus 3 means for this impulse plus rect of t by 2 as the period is 2. See here, the period is 2. This is 2. Okay. Plus 2 into delta of t minus 2. That is for this impulse. Here the impulse is at minus 3, so it is delta of t plus 3, amplitude is 1 and this is rectangular pulse. Okay. Then take Fourier transform. Then your x1 of omega is nothing but 3 into SA of 1.5 omega. There is one identity. Just note it down. Rect of t by t is in pair with t into SA of omega t by 2. This is the Fourier transform pair. If you use this, your x1 of t is rect of t by 3. So you can write your x1 of omega as t into means 3 into SA of t by 2 omega. Here t is capital, t is 3, so it is 1.5 omega. Then what about x2 of omega? x2 of omega. The first term is delta of t plus 3. So the Fourier transform of delta of t plus 3 is e power j3 omega plus, again you use this identity. So it is 2 into SJ of omega plus this one, for this one 2 into e power minus j2 omega. Okay. Then the given y of t equal to x1 of t convolved with x2 of t. We know by the convolution theorem, we can write by the convolution theorem in Fourier transform concept, convolution in time domain is equivalent to multiplication in frequency domain. So according to that, you can write y of omega as x1 of omega into x2 of omega. Okay. Then you can write y of omega as integral minus infinity to infinite y of t into e power minus j omega t dt. You have these two expressions, this one and this one. Make these two equal. Implies integral minus infinity to infinite y of t into e power minus j omega t dt is equal to x1 of omega into x2 of omega. Okay. Now keep omega equal to 0. Implies integral minus infinity to infinite y of t into, if you keep 0 here, it will be 1. So dt is equal to x1 of 0 into x2 of 0. Now what is x1 of 0? Go for x1 of omega. Okay. So what is x1 of 0? So if you keep 0 here, then the value is 3 into, means the amplitude actually. x2 of 0 is e power 0, 1 here, and SJ of omega amplitude 2 plus the delta amplitude 2. So totally what is this? 3 into 5, nothing but your 15. That is the answer. Now the next question is, let x of t be a white Gaussian noise with power spectral density half watt per H. If x of t is input an LTI system with impulse response e power minus t u of t, the average power of the system output is dash watts. Okay. So for that, first consider LTI system. For the LTI system, x of t is input and y of t is output. And the LTI system response is h of t, impulse response is h of t, and given that impulse response as e power minus t u of t, and input power spectral density PSD is given, that is Sx of f is equal to half watt per H. Okay, then you have to find output PSD, and we know the formula. Output PSD is denoted by Sy of f is equal to Sx of f into mod h of f whole square. Okay. Now in this is already a derived relationship between the input and output power spectral densities. Already Sx of f is given, that is half mod h of f whole square. Therefore, output power is equal to integral minus infinity to infinite Sy of f df. That is, just you apply integration here also, half into mod h of f whole square df, half into integral minus infinity to infinite mod h of f whole square df. This is nothing but energy of your impulse response. Now according to Rayleigh energy, even if you find the energy in time domain, the answer is same as that of this. Okay, so you can write, therefore you can write output power is equal to half into integral minus infinity to infinite mod h square of t dt. That is half into integral, what is h of t? E power minus t u of t. So when you are doing for h square of t, yes, as it is unit step function, the limits will be 0 to infinite and the function is e power minus t, okay, whole square dt. So it is nothing but half into integral 0 to infinite e power minus 2t dt. Okay. So if you do this, it will be e power minus 2t by minus 2 between the limits 0 to infinite. Is nothing but half into e power minus infinite minus 0 is totally minus 1 by 4 into, you know, e power infinite is 0. So e power minus 0 is 1. So it is minus 1. It's nothing but 1 by 4 watts. So that is the answer. Now I'll say another problem given in 2021. For a unit step input u of n, a discrete time LTI system produces an output signal 2 into delta of n plus 1 plus delta of n plus delta of n minus 1. Let y of n be the output of the system for an input half power n u of n, the value of y of 0 is. Here in the problem there are two parts. First part is, for a unit step input u of n, a discrete time LTI system produces an output signal of this. Okay. Yes. Then, for the same system, let y of n be the output of the system, for the same system, for input of this. Then, what is the value of y of 0? Okay. So, now take the first part. From the first part, input signal is given. What is the input signal? Input signal is u of n. Okay. Take the system. It is u of n, a discrete, you have to go for a discrete LTI. So, the discrete LTI system response is h of n. Input is x of n, output is y of n. So, the input is given here as u of n. Then what is, as the system is discrete, so to solve this, it is easy to apply Z transform. So what is x of z? X of z is z by z minus 1. Okay. And here output signal y of n is given 2 into delta of n plus 1 plus delta of n plus delta of n minus 1. So again, if you apply Z transform, you will get y of z is equal to into Z transform of delta of n plus 1 is z power plus 1 plus it is z power 0 plus it is z power minus 1. Okay. Then we know for the LTI system, y of n is equal to x of n convolved with h of n. Okay. Y of n equal to x of n convolved with h of n. We know that convolution in n domain or discrete domain is equivalent to the multiplication of their Z transform. So implies, apply that property, y of z equal to x of z into h of z. From this, what is h of z? Y of z by x of z. Simply 2z, z power 0 is 1 plus z power minus 1 by z by z minus 1. Okay. So if you solve this, you're going to get 2z minus 1 minus 1 by z square. This is your h of z. Okay. So you can write it again as h of z equal to 2z minus 1 minus z power minus 2. So now apply inverse z. Now apply inverse z. Implies h of n equal to 2 into delta of n plus 1. For 1 it is delta of n. Inverse z of z power minus 2 is delta of n minus 2. So this is your h of n. We derived h of n from this first part. Now in the second part, for the same system, input is given as half power n u of n, you have to find y of 0. Okay. So what is the second part? This is your h of n. Input is half power n u of n. So from this you have to find y of n, from this you have to find y of 0. So again, from the property of LTI system, y of n equal to, let it be here x of n. Y of n equal to x of n convolved with h of n. Okay. Then what is x of n? Half power n u of n convolved with h of n. Okay. That is half power n into u of n into, that is convolved with 2 delta of n plus 1 minus delta of n minus delta of n minus 2. Okay. Then you have to convolve this half power n u of n with this h of n. These are all deltas. So according to the property of delta function, half power n u of n convolved with 2 into delta of n plus 1 gives you 2 into half power n plus 1. This n now becomes n plus 1 because the delta's indices is n plus 1. Then here also u of n plus 1. And then half power n u of n convolved with delta of n. Okay. Then it becomes simply half power n u of n. Then half power n u of n convolved with delta of n minus 2. Simply it is minus half power n minus 2 into u of n minus 2. So what is this? This is your y of n. Okay. Then how to get y of 0? To get y of 0, simply keep n is equal to 0. Implies y of 0 equal to, yes, n0, 2 into 1 by 2 into u of 1 minus half power 0 u of 0 minus half power minus 2 into u of minus 2. So the answer is, yeah, this is 1 minus half power 0 is 1, u of 0 is 1 minus u of minus 2 is 0 because unit step won't exist for negative value. So totally it is 0. Answer is 0. Okay. So this problem consists of two parts. So for this first part, from this first part, find h of n and give the same h of n to this system, and at that time the input is half power n u of n. You have to find y of 0. Okay, then do that. Y of n equal to x of n convolve with h of n. Simply, this is the convolution between a sequence and the impulse. Okay, so this step is, the step from this to this, it is by the property of impulse function. Fine.
Thank you for watching this video. If you like this video, please don't forget to like, share and subscribe.